In this lesson, we're going to learn how to predict the polarity of a molecule and describe how molecular geometry plays a role in this determination. To determine the polarity of a molecule, we first have to understand the polarity of the bonds, which we covered in the last lesson. When we look at a molecule, we have to look at how the bonds interact in order to determine the overall polarity of a molecule. In molecules that have only non-polar bonds, what we see is that the molecule overall is nonpolar. There has to be at least one polar bond in a molecule for there to be the opportunity to have a polar molecule. When we look at molecules with polar bonds, that means we can have at least one polar bond, and we can have a mixture of either polar and nonpolar bonds, or a mixture of polar bonds with different polarity values as a result of having different elements and different differences in electronegativities. When we look at this, we have to look at the molecular geometry or the electron group geometry to determine how those bonds are interacting to determine the polarity of the molecule. Let's explore this further with some examples. Let's look at CO2. When we look at the Lewis structure of CO2, we see two carbon-oxygen double bonds. We know that carbon and oxygen have a different electronegativity value, so we will see that each of these bonds is considered to be a polar bond. Because there are two electron groups around the central atom, we have a linear geometry, which means we have a bond angle of 180 degrees. As a result, we see that the two polar bonds are directly opposite of one another and are of equal and opposing strength. We can think of this like a tug-of-war game. Imagine we have two teams playing tug-of-war, represented by the red spheres of oxygen, and we have the tie in the middle represented by the gray sphere of carbon. If these two teams are evenly matched, will the carbon atom in the middle move? And the answer is no. If the teams are perfectly matched, everyone will pull in equal and opposite directions. In the case where our tug-of-war game has no winners and no losers, because that middle carbon atom did not move because the teams are evenly and opposite matched, we see that we have a non-polar molecule. Now another example of a linear molecule, HCN. We have a hydrogen, a carbon, and a nitrogen. We know that the hydrogen-carbon bond is considered nonpolar because of the difference in electronegativity values, and carbon and nitrogen have a big enough difference in electronegativity that they would be considered a polar bond. Now, instead of our two evenly matched teams for tug-of-war, we have two teams that are different strengths. We still have our linear geometry and our 180-degree bond angle. But now what we're looking at is teams pulling on that central carbon atom with different strengths. This can happen whether you have a polar and a nonpolar bond or have two bonds with different polarities. As a result, we get a polar molecule because our nitrogen team is stronger or a different strength than the hydrogen team, and as a result, when we think of our tug-of-war game, that central carbon atom will move, and this tells us we have a polar molecule. BCl3 is an example of a trigonal planar molecule because it has three groups around the central atom. Each of the bonds is polar because there's a difference in electronegativity between the boron and the chlorine. But we also see that our bond angles are 120 degrees, everything is evenly matched, so if we imagine there were three teams playing tug-of-war, all pulling on the central boron atom, that middle atom would not move because they're all distributed evenly around the central atom, and all the teams, i.e. the polarity of the bonds, are all the same. Remember, this has trigonal planar geometry, and this is a non-polar molecule. Another example is CH4. Remember that CH forms a non-polar bond, so all the bonds in this molecule are non-polar. Because there are no polar bonds, we cannot possibly have a polar molecule. So this is also a nonpolar molecule. When all the bonds are nonpolar, the molecule is also nonpolar. A similar example is CH3Cl. One of the hydrogen atoms has been replaced with a chlorine. We know that we have some polar bonds and some nonpolar bonds. All of the CH bonds are nonpolar, but we know that the CCl bond is polar. So now we need to imagine our tug-of-war game, only now we're playing in 3 dimensions. Tetrahedral geometry does not occur in a single plane, so we need to think in 3 dimensions. As a result, our one team has a different strength, so the carbon-chlorine team has a different strength than the other 3 teams, and if they were all pulling, what we would see is that central atom would move. As a result, this is a polar molecule. And this is an example of why you need to understand and be able to picture the tetrahedral geometry in your head so you can see how these bonds are playing together in order to form a polar or non-polar molecule. NH3, also known as ammonia, also has a tetrahedral geometry because it has that lone pair which gives it 4 groups around the central atom. We see that each of the NH bonds are considered polar bonds, but remember this has tetrahedral geometry with our 109.5 degree angles. Even though there are only 3 bonding groups, we need to still consider this as a tetrahedral. And with the lone pair, we can imagine is the team that just walked away from our tug-of-war game, but the other 3 teams did not change their positions. As a result, they are now still pulling, but there's no counter to pull back in the other direction, and so those 3 polar bonds result in this being a polar molecule.